And today I'm going to give you a lecture because Professor Boyd has some problem with some health problem. So I'm here to help him and also help you to understand the lecture. So we can start now. Yeah. In the previous lecture, you have learned about the critical point. Let me recall some key point from the last lecture, so you can follow today's lecture smoothly. Let me recall what is a critical point. So in calculus 1, for one variable function, you have already learned what is a critical point, right? And now we have this very similar object for the multiple variable function. So critical point contain two type of point. The first one is singular point. Singular points are the interior points like that. You have the partial derivative with respect to x. Yeah. Okay. fx and fy do not exist, not equal to 0. Fx or fy do not exist. Then you have the so-called singular points. And you have the second type, the stationary point. The other points such that the gradient vector of f attains 0 value. That means you have both partial derivative with respect to x and with respect to y are equal to 0. Okay. But keep in mind that critical points should be interior point. Okay. So you know we have two types point, boundary point, three types: boundary point, interior point, and outer point, exterior point, depending on the domain of the function. Okay, so we also have learned that how to find the critical point, right? By analyzing the partial derivative. And now, today, we are going to use the partial derivative to find and classify the local extremum and local extremum of a function of, for example, two variable function. That can be considered a generalization of the derivative test you have learned in calculus 1. But now we have used for the two variable function. Okay. So we are going to use partial derivative to find and classify the local extremum yeah, in the last lecture you have introduced also what is a local extremer. We have two types of local extremer. That is the minimum and the maximum. When we consider only the value of the function only in a small area, region around a given point, then we have the so-called local extreme. And now we are going to find it using the second order derivative test for local extreme. Okay, so take a look on this theorem. You will see how to use the partial derivative up to the second order to classify the critical point. So first we need some assumption before we proceed. We suppose that the second order partial derivative of f is continuous. Okay, in an open disk center at the given point AB, and such that the gradient vector of f at AB equal to 0. That means we have here some stationary point, right? It is actually the definition of a stationary point. Okay, so we want to know if this stationary point is a local extremer point or not, right? So let's consider discriminant of a function f at AB. We denote it by the letter capital D, and here is the formula to calculate discriminant of D of f at AB. I will show you another form of this formula that might help you to remember this expression easier. So, okay, so at this step we should accept, you should understand that this formula, this expression gives you a number, right? When you know the function f and the point AB, you can find the value of this discriminant D, right? And now we are going to consider the sign of D and the second order partial derivative of f at AB with respect to one variable x. So you can see in the first statement, if the value of D is positive and the second order partial derivative with respect to x is also positive, then the value of f at AB is a local minimum. Okay. In the second statement, if we have the condition of D and f at x, in this case, f(x) at AB is negative, then fAB is local maximum. So you can in the first and second statement, you can see that we don't have the case when the second derivative is 0, right? Because if the second order derivative is 0, then substitute this value to this formula of the discriminant. You can see that the discriminant should be non-positive, right? That is not true with that make a contradiction with this assumption of the positivity of the discriminant, right? So there is not the case when the second order partial derivative is 0. In the last case, when we have negative discriminant, then the value of f of AB is not a local equivalent. In this case, in fact, it is the point AB is called the saddle point. You know from the last lecture, when a stationary point is not a local equivalent point, then it is called a saddle point. You have a theorem that says that if the function f has a local equivalent at an interior point and the interior point AB, and that point is a stationary point, then it is okay. So I'm sorry that if the function f has a local equivalent at an interior point and the first partial derivative fx and fy exist, then this interior point AB is a stationary point. Okay? That is a very important theorem. However, this theorem doesn't tell us that all stationary points are local equivalent. That is the reason we have this second order derivative test. You know, there are cases when the stationary points are not equivalent point. And in this case, the point is called the saddle point. Okay? So we are going to use this to practice using this test to classify the stationary point. Okay, so in this remark, you will see another way to remember the expression of the discriminant. You can see that you can rewrite the expression of a discriminant in the form of a determinant of a matrix. And here you can see that we have some component of a matrix that is quite easy to remember, right? And using the definition of a determinant, you can see that it is nothing but the product. Yeah, let's rewrite minus fxy fyx. And remember that in previous lecture, you have a so-called Clairaut theorem telling that in some case you have equality of fxy and fyx, right? If the function f satisfies some not so special condition. In the second remark, you can see that in the first case, when the discriminant is negative, point AB is a saddle point, as I mentioned previously. Okay, you might ask the question: what happens if the discriminant is 0? And here's the answer: you have no information. That means it is inclusive, inconclusive. Okay. So now let's continue with an example. First, I will give you an example to recall you how to. Okay. Give you an example to recall you how to find all the stationary points. and then we are going to classify them. Okay. Let's consider the example. That is a continuation of example 9 in your lecture note. So we are given two variable function f x y equal to y squared minus y to the power 4 minus x squared, and we need to classify all stationary points cause the stationary point of this function. So first step should be we should find all the stationary point, right? Step 1. We need to find all stationary points. And you know, if we want to find the stationary point, we need to consider the first order partial derivative, right? That means we need to find fx, and you can see if you want to calculate the partial derivative with respect to x, the idea is keep y as constant, right? So you have this, right? And similarly, fy equal to 2y minus 4y cubed, right? So to find the stationary point, you need to solve the system of equation fx equal to 0 and fy equal to 0. So that is equivalent to 2x equals 0, 2y multiplied 4y cubed equal to 0, and easily you will get the solution x equal to 0 and y equal to 0, or y equal to plus minus 1 over square root of 2. You agree? So you have here 3 stationary points: 0, 0, 0, 1 over square root of 2, 0, minus 1 over square root of 2. And of course, you can see with the given function defined in the whole space R2, right? So the domain is the set R2. That means the points are interior points. You agree? They are interior points, and such that the gradient vector at the point are equal to 0. So we have stationary point. That is the first step. In the second step, we need to classify, or you can say we need to see if we can say about the property. We want to see if we can conclude about the local extreme property of the point. So we are going to use the second order derivative test. So we need to find the discriminant d, and also the second order partial derivative of f with respect to x, right? That means we are going to find fx, fy, fxx, fyy and fxy in order to calculate the discriminant, right? Okay, so let's see. Okay, so we have fx equal to minus 2x and fy equal to 2y minus 4y cubed. So let's calculate fxx has minus 2, right? Fyy equal to 2 minus 12y squared. And fxy equal to fyx, you can easily verify this equality, and it is equal to 0. Now, let's take a look on the formula of the discriminant. In the remark you see, to remember it, you can use a form of determinant of a matrix, this form. Right? And using the definition of the determinant, you have this formula.
Minus.
Right. That is easier to remember, right? And just substitute the above value of second order partial derivative. You have the value of the
Minus 4.
discriminant of the. Okay, so
Yeah, this.
the general point xy, this discriminant take the values. Let's see, 2 fxx is minus 2 multiplied with 2 minus 12y squared and minus 0 squared. And we have here 24y squared minus 4. So now let's consider these stationary points one by one using the second order derivative test. So we consider the first point 0, 0. Okay. So we need to check the sign of the discriminant and the second order derivative with respect to x at 0, 0, right? You can easily see that b0, 0 equal to minus 4, right? And fx 0, 0 equal to minus 2. And you know that in the case when we have negative value of discriminant, we have a saddle point. Is a saddle point. That is the first point. Okay, you get it? The second point, 0, 1 over square root of 2. The discriminant is equal to
12.
okay, 12 multiplied with 1 over square root 2 whole square minus 4, right? And it is equal to 8, right? And it's positive. Now we need to check the second order partial derivative fxx at 0, 1 over 2 square root 2. And you can see that this second order partial derivative is a constant number for every xy. It is minus 2 less than 0. So let's take a look again at the second order derivative test. So it is the second case, right? When the discriminant is positive and the second order derivative is negative, then we have local maximum. That means f at 0, 1 over 2 square root 2 is a local maximum. Okay. Or you can say that the point 0, 1 over square root 2 is a local maximal point. That means the point where the function attains the local maximum, right? You can do similarly for the remaining point 0 minus 1 over square root 2, and you can see that it is also a local maximal point. Okay. So I have already shown you an example of how to use a second order partial derivative test. Okay, second order derivative test to classify the stationary point. Okay. So you can see there is a solution that you can read again later. So let's do one more example. Okay. So now we consider the function, the example 12. The two variable function x to the power 4, y to the power 4 minus 4xy plus 1. And you need to find the local extremum. So now we need to find all the critical point, right? And remember, you should remember that the critical point contains singular point and stationary point. So anyway, we need to consider the partial derivative. So that means we need to calculate the gradient vector of f. Okay. And you can easily see that it is a vector of two components corresponding to the fx and fy. So fx is partial derivative with respect to x. You have is 4x cubed minus 4y right. And fy is 4y cubed minus 4x. So you can see that the partial derivatives are always defined. So we have no singular point. We can only find the stationary point. Expect to find stationary point. So we need to consider the equation of gradient vector of f equal to 0. That means that is equivalent to fa is equal to 0 and fy equal to 0 to find the stationary point. So, using the previous formula, you have this. Agree? So, now that is problem of solving a system of equations. We first need to simplify the equation. Right. It's almost step. And of course, from the two equations, you have a consequent equation. You have just substitute the value of x. You have, from the first equation, you have y equal to x cubed, right? And substitute it to the second equation, you have 8 to the power of 9 equal to x, right? We need to solve this equation. It is very easy, and there is familiar to most of you. We use the factorization of polynomial. So let's see. The first common factor is x. Then we have x to the power of 8 minus 1, 0, right? Now using some very famous identity for high school, you can easily factorize this as follows. So I only give you the final form of the factorization. Okay? So we are going to find the real number, a real root of this equation. So we don't care about the complex number. Right? That means x can only take the value 0, 1, or minus 1. Right? You see? So that implies 3 stationary points: 0, 0, 1, 1, and minus 1, minus 1. Okay. Now we come back to the previous example of classifying the stationary point, and we need to calculate the discriminant and the second order partial derivative fxx at the stationary point. Then compare it with the conclusion of the second order derivative test to see if we have local extrema or not. Right. Okay, so let's do it quickly. Now I am not going to give you again the alternative form of the discriminant of this one. Okay. So we need to find fxx. So what is our function? So our function. Okay. So here's fx. This one is fx. This one is fy. So fxx is 12x squared. Is 12x squared. And fyy is 12y squared. fxy is minus 4. Right? So we have enough information to find the formula of the discriminant, right? We have here 144 x squared times y squared, right? Minus we have this one. Squared. Sorry. minus fxy square means we have here minus 16. Okay.
Rẻ hơn nhiều.
So now the first step we need to consider the stationary points one by one. Okay. So let's consider the point 0, 0. For example, you have the discriminant 0, 0 is equal to minus 16, which is negative. So in this case, we have a set of points, right? Okay, is a point 1, 1. The discriminant is, because it is positive, it's clear. We need to check fxx 1, 1. And we have value 12. So in this case, we have local minimum. Right. That means the function f attains the local minimum at the point 1, 1. You agree? You can say f1, 1 is the local minimum f, right? So similarly, you will get the local minimum for the point minus 1, minus 1. We're going to do it now. Okay? So I hope that help you to understand how to use a second derivative test for this problem. You can see here the proof of example 12. Okay, so far we only consider the local extremum. Now we are going to talk about the global maximum or global extremum that contain global maximum and global minimum value of the function f. First, we need the definition of what is a global maximum and what is the global minimum. So you can see that it is very easy to understand the definition. In the part A, if a function f of two variables has a global or absolute maximum on its domain D, and the point A, B is a point in the domain of function, of course, right? But in this case, it does not need to be an interior point. Okay. So if the value of f at any point in the domain of the function is less than or equal to the value of f at a, then this value is local and its global maximum value of f on its domain. It's quite easy to understand, right? And it's very similar to the definition of absolute maximum and absolute minimum in calculus 1. Right? So in part B, you have the definition of global or absolute minimum in a very similar way. Right? Okay, so let's take a look on this example. We are going to use only the definition of global extremum to find the global minimum of this given function. Okay. So we are going to find the global minimum of this two-variable function, x squared plus y squared minus 2x minus 6y plus 40 on its domain is R2, right? And here's the solution. That is the way we do in high school, right? We prove the given function is always greater than or equal to some number, and find the points x, y where we have the equality. Okay. So using some very well-known identity, you can see that. Let me recall. We are going to use this type of identity. Right. You have learned it in 8th class, right? You agree? So let's consider the function. You have x squared minus 2x, so we need to add 1 to have this square expression, right? Then for y, you have y squared multiplied 6y. Now let's factorize. You have 2y multiplied with 3. So you should add number 9 here to have a square expression. So now we still have 4 as a remainder. And you can see this one gives you x minus 1 all squared. This one gives you y minus 3 all squared, right? And here's the remainder, 4. Okay, so now we agree that we can revise the given function in this form. And using the non-negative property of Z2 squared number, you can see easily fxy is always greater than or equal to 4, right? For all x and y. That's clear, right? So we still need one more step to conclude. Number 4 is the global minimum. We need to find the point x, y where we have the equality. Otherwise, the number 4 is not a global minimum. That is the reason we have this sentence. The equality occurs when we have Z2 square number are equal to 0, right? So you can easily solve the Z2 equation to get x equal 1 and y equal 3. Okay? So this function, the given function, obtain global minimum at x, y equal to 1, 3. And the value of the global minimum is equal to 4. Okay? That is an example of global minimum of two variable function. Using just only the definition. Okay? Okay, so now we discuss about the existence of global maximum and global minimum. Okay? In general, the global maximum and or minimum of a function may not exist unless we consider a very nice domain of function, or a function on a very special set of value of x, y. You can see in this line, when the function f is continuous and the domain of it and its domain satisfies some nice condition. Here's we will see what is nice condition mean in the next slide. Then the existence of global extremum is guaranteed. Okay. So you can see here is the condition for the existence of a global extremum. The domain of the function should be closed and bounded. Okay. So when you have a set, when you consider a continuous function on a closed and bounded set, then it is guaranteed that the global extrema exists both maximum and minimum. Okay. So here is some example of a closed set on R2. You can see closed is very easy to imagine, right? Here is closed set, and here are the set which are not closed. You can see we have some gap. That means you can move from inside to the outside, right? And it is not closed. Okay? So what bounded mean? Bounded mean you can cover this set by a circle, a finite radius. For example, you see it is easy to cover this set by a bigger circle, right? So you can easily understand the word bounded in this way. So let me show you another example of a closed and bounded set. Let's consider only the circle, not the interior point. This is also an example of closed and bounded set. You understand? I only consider the point along this circle, not the point inside or outside. This is also an example of closed and bounded set. Okay? So now, if we know that if we know about the existence of global extrema, then we have a method to find the value of global extrema. So we move to the next topic about the optimization problem. Okay, before going to the mathematical form, we have here some example show you the very important role of this topic in practice. So in real life, you have many problems that require you to find optimized solution, right? If you want to move from the point A to the point B, you need to find the shortest way or fastest way to move from A to B. This is an example of an optimization problem. Okay? And we have so many forms of optimization problem. In the example, you can see that some example of optimization problem. Written in mathematical form. Okay. So normally in practice we have a real life problem. Then we need to transform it or written it in the form of mathematical problem. Then we have an optimization problem. We need to solve it, right? So we are here in the second step when we already have mathematical form of an optimization problem. Okay? You can see in the first example, we need to find the shortest distance from this point to this curve. Okay. Whenever you see a problem of finding shortest or minimum, the extrema value of a function, then you have an optimization problem. Okay? so before we move to the next slide about the Lagrange multiplier method, maybe we need to take a short break.
Kèo học ở kèo thi lại. Nếu mà thắng thì bây giờ mày tính mày thua thì mày trả nốt tiền thi lại.
Đúng rồi. Thua mất trong thắng được triệu 6.
Thắng thì mất tiền thi lại. Mày Phú bác máy đi quay cho anh cái ngày lịch sử này. Ai? Đâu?
Lên được.
Lên đồ. Bác máy đi quay cho anh. Có người quay. Anh Tùng chắc Tùng mắt là
Không. Cái kèo 100 vàng chặn năm.
có hết 200 thì
Chặn 500 một ván. Chưa? Chưa?
cho ta đấy.
Chặn 501.
Mày bị điên thì mày thế mày biết bắn như một ván như nào không? Một ván thì mẹ con quay ở trên bàn ấy, một ván đâu ngươi nhé mãi đầu
Có 15 thì chừng ấm
dưới
đây.
thế
Chặn từ bàn nhá.
còn ra đây đấy xuống còn 50 đâu
Lại hơi hề.
50 thì đéo có tiền đâu với thân
100% qua tôi có 290.000.
đến đây chia bao lứa
90.000 nhưng mà con cười cũng được. Chặn 6.2 bàn. Chưa? Chặn 2 bàn.
này
Chặn ít thế. Chặn 2 thì tôi cũng chặn 6. Biết thua sẵn này. Chặn 6.2 thêm 4 ván nữa.
เอาđi đi mẹ đi nhanh à
Đi đâu?
rủ thêm người đi
Chơi con gì mà tao biết chơi đâu.
bây giờ nhá em việc bắn anh Tùng bảo xong về anh Tùng bảo anh Tùng trước và đéo nữa
Không, ông kèo mà trong này kèo biết không, anh Tùng hay nhiều tiền, anh Tùng không số em chuyện này đâu chuyện
đéo chơi mày đéo phải kinh trường
thế chơi hôm nay biết mở anh đi luôn này. Thấy em Việt còn gì Nhật Bản không? Thì nhận gì? Không, chỉ cái tiền 70 không? Thì rồi,
để ba hai thằng bắn chán lắm mày lại lý do
cho vui, bắn cho vui, cho kèo mà cho đeo vui. Biết bắn này.
đây bây giờ nhá tao lúc này thì với cả thế thì bây giờ tao với mày bố với Tùng chơi không bây giờ Tùng mình Tùng phải chắc hai đó bởi vì em bắn là chắc là khoảng 50% anh Tùng thằng này 25 thằng này zero rồi
Hai anh em mình bắn chán thì chưa là cái tiền rồi. Ba
nghe suy ấy
kèo 73 kèo 73
mà suy quá
63 thơm không thơm không thơm luôn.
anh ấy con bạn này biết mình vừa chuyển tiền đấy
Thơm
tao mà 100.000
cái cả thế
bây giờ tao hỏi mày nhá
mình đi
đấy là số gì đấy 30% là 70%
ba mà sợ sợ tiếp tiếp dấm đá đầu áp đi đâu may mắn
hai lồn sáng
tôi thấy bạn vẫn nhiều mà
dạ sao rồi không bao cũng bị chém con ba chẳng giáp mặt tự sẽ đẹp à
hay mà
nhưng mà hôm nay thì phim
anh người cũng vào học
đi vào trường đi tôi
đi qua cũng bị cài cắm
nhờ này có phải lồn bao lâu rồi
xong cấp này có không thì ngọc là rất là có không này cũng phải bắt học rồi bỏ ăn rồi
bắn mấy ở
bắt học bao chưa cũng được
tròn lỗ quá to quá
chưa hay là ba là
90 không 73 63
Thôi, 90 của mày cũng nói à? Đang có tiền của mày mày tính à?
là 63
60 nghìn cho cháu mày đi.
nghe nó suy quá
đấy mẹ mày rủ bố mày lần nữa hay không
anh còn chưa vào nhưng có không là nhận này đeo cặp này
mày rủ bố mày lần nữa hay không
đeo cặp này đi
Thì cũng được. Nhưng trường khác không phải trường mình.
anh nghĩa quá
dạ thắng rồi thắng là dục vọng của bản thân rồi là bố mày hôm nay muốn đi học thắng được bản thân rồi không được
chán thật ra cửa mà có thang máy rồi em Việt bảo là cô vào đi
nóng vãi rồi
em Việt bảo ra ngoài đến mà trong ngồi hòa mát chán em Việt thật
bây giờ nhá thì mẹ ngày xưa con đường rồi là chỗ nào của con đường thì mẹ chỉ mẹ vào mùa đại học để tao thì tao chẳng thắng tao
Okay, so let's continue.
đấu hết đi nổi giờ
tại anh ra thang máy có thang máy rồi
Are you ready?
ngon thì mua là nhiều
Now we are going to see how to use the method Pro Lagrange multiplier to find the global picture with constraint. Here's the first form of a Lagrange multiplier with one constraint.
này chữ em chữ
So
phải nghĩ
we are going to discuss the method of Lagrange multiplier for maximizing or minimizing a function f of x and y, subject to a constraint of the form gxy is equal to k, equal k, right?
viết đuôi đâu
So here's a general form of this optimization problem, where f is the given function for which we want to maximize or minimize, and g for g equal to k form the constraint. Okay. So this is the first and very important step whenever you want to use the Lagrange multiplier method. You need to form your problem in this way to decide what is the function optimization function the function we want to optimize and to decide what is the constraint. Okay. So here is an algorithm of the Lagrange multiplier method. Of course, we need to assume that the global extrema with the constraint exists. Then it makes sense to consider the next step. If you can prove that there is no global extrema, so there is no reason to continue with the Lagrange multiplier method, right? You agree? So here, let's take a look on this algorithm. We will see that, and we will try to adapt this algorithm to find the global extrema for in some example later. Okay, to find the maximum minimum value of f subject to the constraint g equal to k, we do the following step. Step 1, we need to find all value of x, y, and lambda satisfy the two equations. That is the reason I told you to be sure that you have this first step so you won't confuse about the function f and g. Okay? Because if you are confused about f and g, then this one will be wrong. Okay? So we need to find all the value of x, y, and lambda such that we have the gradient of the vector gradient of f equal to have this equal to lambda multiplied by the gradient vector of g. And of course, this constraint should be satisfied. So assuming that you finish the step 1, where you have the value of x, y, and lambda, then you move to the second step. We evaluate the value of f at all points x, y we found in the first step, and comparing all of the value, then the largest value is the maximum value, and the smallest value will be the minimum value. It's very similar to the second step of a closed interval method from calculus 1, right? You remember that? In calculus 1, you have a method to find the global extrema of one variable function. That is called the closed interval method. And the last step of that method, we also need to compare all value of function f. Right. Okay. So here is some remark. When lambda equals 0, then we have the vector gradient vector of f equal to 0, right? Then we have some stationary point of f. If lambda is non-zero, then the two vectors are parallel. This one should be the gradient vector of g, right? So you can see here is the diagram describes the case when two gradient vectors are parallel. And from previous lecture, you know that you have learned the orthogonality of the gradient vector to the tangent line or the tangent surface, right? Tangent plane of the curve or surface, right? And you can see when two gradient vector are parallel, that means there exists a level curve of the function f such that we have the common tangent line of the level curve g xy equal to k and f xy. In this diagram, the level curve of f is f xy equal to 10. They have the same tangent line. Okay, that is a geometrical meaning of this relation between two gradient vectors. Okay. So now we are going to adopt this method to find the extreme values of this given function on this circle. Okay. So you can see here we have on the left side the graph of the surface given by this two-variable function. Of course, we restrict it on this circle. Right. Here is the circle x squared plus y squared equal 1. Okay. This one is a 2D view of this graph when you look at from below to the xy plane. Okay. So we are going to use this Lagrange multiplier method to find the extreme value of this function. Okay. See, let me rewind the function. So we have f xy equal to x squared plus 2y squared, and we want to find the extreme value on this circle. X squared plus y squared equal 1. So note that it's important to remember that we only consider the value of the function f along the circle only, not inside the circle. Okay? So if you remember, I mentioned before, this circle is an example of closed and bounded set. You agree? The circle x squared plus y squared equal to 1 is an example of closed and bounded set. I mentioned it before. So, using the theorem in previous topic, you know that if this function is continuous, then the existence of global extremum is guaranteed. Right? So that is the answer for this first line of the end region. We assume that we know the existence of a global extremum. That makes sense now to consider the problem of finding the value. Right? Okay, so this one is closed and bounded set, and the function f is continuous. The domain of this function is a whole space R2. Right? So, is satisfied the assumption of the previous theorem, then global extremum exists. By global extrema, I mean global maximum and global minimum. Not only one of them, right? So now we are ready to process the multiplying Lagrange multiplier algorithm. So step one, we need to state the general form of optimization problem to decide what is the optimization function, optimize function, and what is the constraint. So here's question F, x squared plus 2y squared. We are going to find the maximum and the minimum, and the constraint gxy equal to the equation of the circle, and the value of k is 1. Right? Now we know the constraint. That is a very important step. Okay? So now let's consider a system of equation. The gradient vector of f is equal to lambda gradient times gradient vector of g. And the second equation is gxy equal to 1. Right? Now we need to decide what is the form of this equation. Of course, we need to find the gradient vector of f, right? So we have here fx equals 2x and 4y and equal to lambda multiplied by gradient vector of g is 2x, 2y, right? And gxy equal to 1 means x squared plus y squared equal to 1. It's clear? So, comparing two components of the two vectors, one by one, you get 2x equal to lambda multiplied by 2x, 4y equal lambda multiplied 2y, and x squared plus y squared equal 1. Okay. Now we are going to simplify this system of equation. So we have x equal to lambda times x, y, 2y equal to lambda times y, and x squared plus y squared equal to 1. We need to solve this equation to find all the value of x, y, and lambda. Okay. So from the first equation, you know that it is equivalent to x minus 1, x multiplied by 1 minus lambda in bracket equal to 0. So from this equation, you know that x equal to 0 or lambda equal to 1. We have two cases, right? So if x equal to 0, then from the first equation, you know y equal to plus or minus 1. Right? Because y squared equal to 1. Means y equal to plus or minus 1. If lambda equal to 1, then from the second equation, you know that 2y equal to y, right? And from this equation, you have y equal to 0. And then substitute it to the third equation, you get x equal to plus or minus 1. You agree? Just a program of solving a very simple system equation. So now let's summarize what we have. For x equal to 0, we have 2.01, 0 minus 1, right? If lambda into 1, we also have 2.10 and minus 10. You agree? And now we can move to the second step. If you want to find the global maximum, let's find the greatest value of f among the four points.
Tiền nhiều quá, tiền bớt.
Step 2. We need to evaluate the value of f at the point. And f01 equal to f0 minus 1 and equal to 2. F1 0 equal to f minus 1 0 equal to 1. So you can see that here this is the maximum, the global maximum, right? Minimum value. Understand? Just follow the algorithm step by step. You see that it's very easy to find the extrema with constraint. Okay. You can also read it again in the lecture note. You see, you have lecture note and you can read it again. Okay. So let's move to the optimization problem for three-variable function. So let's see if we can proceed similarly or not to this three-variable function. And you can see here the algorithm for the Lagrange multiplier for three-variable function. It's quite similar to the. Indeed, it is the same algorithm as for the two-variable function. And in the first step, we also need to assume that we know the global extrema exists. Okay. Then step 1, we need to solve system of equation comparing two calibrate the optimization function and the constraint function. And then evaluate the value of f at the point you get from the first step to conclude the global maxima and global minima. So let's consider this example. So we are going to consider this example. We are given a rectangular box with our link. So to do this kind of problem, you need you are here in the first step. What I mentioned at the beginning of this topic, you have a real problem, and now you need to form it as a mathematical problem. Okay? Of course, if you want to do to have mathematical form, you need to understand the object. Right. So rectangular box with our lid has this form, right? It's quite easy to understand. So assume that we don't have lid the upper lid, right? So this one is empty. We can do it by cutting the four corner of a cardboard, right? I think you should remember this problem because we have an exercise in calculus 1 at the beginning of the calculus 1 course that we cut out the four corners of cardboard to build, to create this type of rectangular box without the upper lid, right? You understand? Okay, so a rectangular box without lid is to be made from 12 meters square cardboard. Okay, so that means this cardboard has the area of 12 meters square, right? The area of the cardboard is 12 meters square. And we need to find the maximum volume of this ball. Okay, see how we do it. Okay, so now we need to maximize the volume of the box. So the function to optimize should be the function of the volume, right? If you want to calculate the volume, you need to know three dimensions of this rectangular box, right? The height and the width and the length, right? So because we are working with functions, so I'm going to use the letter. It's better to use the letter x, y, and z, not a, b, and h. So assume that x, y, z denote respectively the length, width, and the height of this rectangular box. You agree? So x and y and z should be positive, right? That is the first thing you should be careful. Find the condition of all variables. So the volume is given by the product of the three dimensions. Right? This is the formula to give you the volume of the rectangular box. You agree? And this is also the function we want to maximize. In the next step, we need to find the constraint, right? From the assumption of the area of this cardboard. So let's take a look closely in this picture of the cardboard. X is the length, and it should be this side, and this one is y, which is the width, and the height is given by this side of the square of the corner, right? So from this interpretation or explanation, you are able to find the formula of the area of the given cardboard, right? The area should be given by function a, x, y, z, and it is equal to okay, so the cardboards have two dimensions, x plus z multiply with y plus z, right?
là mày ôn rồi con mày chụp cái là mày sẽ
Okay, so
đầu tiên mày của nhà ta
sorry,
dồn không rồi một thằng mày để lại hai thằng suốt không ra ngoài
sorry, maybe I made mistake.
mà thường thì nó sẽ cắt cái ví dụ nó sẽ cắt theo phần trăm ví dụ mày rút 1 triệu ăn khoảng 10 20 nghìn thì
Exceed the square. It should be x plus 2z and y plus 2z, right? You agree? This side is x plus 2z and this side is y plus 2z, right? Is correct? So let's see what is this function. Is equal to okay, so we come out four corners, so we need to subtract the area of the four corners, right? You agree? We cut out the four corners to make the box, so we need to subtract
Việt Nam đều chơi
the area of the four corners, which is given for the square. Because they are square.
bác nếu mà mày chơi mày nói rồi mày là nếu mà mày có quyền
So it is
mày liên quan
geometric problem, right?
không mày sẽ là đi về đồng loại
So let's see what is the function of the constraint. xy plus
hai nhà đầu
2x
sang Campuchia đánh bài suốt
yz plus 4z square minus 4z square. So you have this function 2xz plus 2yz plus xy. This function gives you the area of the cardboard after cutting four corners. Or this one is equal to the area of this rectangular box. Okay, you can see that it is the summation of the area of the rectangle, right? Without the upper lid. Okay, so in general, after this, I'm saying, after this analyzation, we get we can now revise this problem as a mathematical problem. So we want to maximize the function v of x, y, and z. That is a volume function, right? And we have the constraint. This is function a. The area function is given by 2xz, 2yz plus xy.
mình tưởng là học nó dễ thôi à
And keep in mind that we consider only the case when x, y, and z
mưa dầm
greater than 0. Okay? This one is completely
đấy là nền đất thôi trên nền
a
bên
mathematical problem. Right? So We are here in the second step,
máy kéo vào trước
optimization problem. Okay, so let's
thằng này có
use
trên đời này có cái gì ở trên trời
the
không?
algorithm of a Lagrange multiplier for three variables. So you know, this one should be equal to 12, right? That is the constraint.
Để trường
So you know this one is
6 giờ
a closed surface, right? Yes. Correct. It should be close and about set. So assuming that we know the existence of the extreme, we are going to use the Lagrange multiplier. So let's go to the step one. First step, we need to consider this system of equation. We compare two graded vectors.
tao
Right.
chơi với thằng của bạn phải không?
And the second equation is A equals to 12. Okay? So let's see what is the gradient of B. So let's write in the form of a vector. So the partial derivative with respect to x is yz, to y is xz, and the last one is xy, right? It is a gradient vector of function v. And it should be equal to the lambda times gradient vector of A, which is,
Đầu tiên thì lại
let's see,
chưa thế có triệu tôi vay nào
2z plus y, right? Partial derivative
bao giờ
with respect to x. And now we see the second one, 2z plus x, and the last one is 2x plus 2y, right?
ôn gì chưa?
Is correct. So a equal to 0 means we have this equation.
Mẹ này chuyển 500 đưa 500 đây tôi cũng đánh không đúng.
So let's recite this
Mày 500 để đi mua đồ cho bà
system
sao?
of equation. We have yz equal to lambda multiplied with 2z plus y,
Vì nếu con phải xe thì
xz equal to lambda times 2z plus x bracket cos xy is lambda times 2x plus 2y, and the last one we keep this form. Okay. So you see we have a system of four equations with four variables x, y, z, and lambda, and we want to find the value of x, y, z, and lambda. Okay. So let's try to solve this system of equation. How to do it? We should use a simple trick. You see that if you multiply the first three equations by x, y, and z, you have some equality, right? So let's do it. Let's multiply the first three equations by x, y, and z respectively. So we will have x, y, z equal to lambda 2xz plus yx, right? x, y, z equal to lambda 2zyx plus xy, and x, y, z equal to lambda 2x plus 2xz plus 2yz. Now you can compare the the couple of equations. Right. Let's consider the equality of the first two equations. You will have lambda equal to, so we have this, right? The first two equations. You agree? Now there will be two cases. What happens if lambda equal to 0? If lambda equal to 0? So if lambda equal to 0, so we come back to the original form. We see that yz, xz, and xy are equal to 0. Do you agree? If lambda equal to 0. So xy equal to xz equal to yz equal to 0. So it makes a contradiction with the last equation. Right? In the last equation we have this something equal to 12. So if all terms are 0, you don't have this equation. Do you agree? So you don't take it right. So lambda is non-zero. So if lambda is non-zero, then you have 2xz plus yx equal to yz plus xy. Okay? Comparing this equation and this equation, you also have 2yz plus xy equal to 2xz plus 2yz. So this system is equivalent to you have xz equal to yz, and what do we have here? Xy equal to 2xz. Okay? So that is equivalent to x equal to y and y equal to 2z. They should not be equal to 0 because otherwise the last equation here will not be satisfied. So that is the reason we have the relation. Okay, so it is quite long, but when you have this relation, you can easily find that z squared equals 1. When you substitute the relation into this equation. Okay. So let's say we can find out z squared equal to 1. That is it. And keep in mind that we assume z is positive, right? So z can only be equal to 1. So let's come back to find x and y. You have x equal to y and equal to 2. That means from the first step we only find 1 point. This one, right? So if we want to do the second step, remember that we need to compare the value of f at the point we get from the first step, right? But we have only 1 point. So how do we know if this one is global maximum or global minimum? Do you have any idea? We have only 1 point and we don't have other points to compare. So how do we know if this one is global or minimum? It's very easy. Just take the arbitrary point, satisfy the assumption of the problem and compare it with the the value of b at this point. Okay. First thing, you still need to find the value of the volume with the 3 dimensions. It is equal to 4, right? So now I take an arbitrary point such that we have the function such that we have a 2, 1, 5 equal to 12. So let's find the value of b at this point, and it is equal to 10. This one is less than this value. That means this value should be the global minimum.
Hơi tham, tôi bảo cái bài cốt thì
Maximum.
em
Sorry.
3 lần tài.
Okay. It is, we know from the first step, we know it is a global maximum or global minimum. And if we want to conclude in the second step, we need to compare it with a value of the b. Right? So we choose a suitable point and compare value of b at each point. Okay. So it's final, but maybe you get a general idea. You can read and try it again because you can also have the solution in this lecture. Okay. So we still have time now for the last topic, just to introduce to you a new object, the double integral. You can see in this slide, we recall the definition of a definite integral in N+1, right? And keep in mind that, remember that we have the rigorous definition of the definite integral using the Riemann summation, right? Okay, so for this definition, you just recall the definition from N+1. And here's a picture. Here is an important picture that shows you the original motivation of deriving definite integral. Take a look on this picture. If you have a graph of function fx, we assume that it is this curve. And we consider the function f on a given interval from a to b. You see, we have a set region under the graph, right? Okay? Under the graph of function f, you have a region, set region. And the question, number one question is, can we find the area of this region? Right? The answer is the definite integral gives you the area of this region under the graph of function f and go x-axis. Okay? I hope that remind you about the meaning of definite integral in N+1 course. And you can see here we have some rectangular. The rectangular are generated from the sample point we take in the construction of Riemann summation. So the idea is to, if you want to find the, so before you know the definition, before you have the definite integral, you don't have anything to calculate the area of the region I mentioned, right? And now they try to use the rectangle to approximate the area. Okay, you can see that it is not equal, but if you have more and more rectangular, the two regions will be very close. That is the reason we have a limit. When we increase number of sample points, here are some sample points, and you can approximate the volume of the area by the sum of area of the rectangle. That is the idea of deriving the definite integral for one variable function. So keep in mind this idea, you can derive very similar object for two variable function. Okay? First, take a look on this picture. This blue area is give you the graph of two variable function. It is a surface, right? This one is a surface, a graph of function, two variable function f. And we consider this two variable function on a domain D, a region in xy plane. So the very similar question we can ask is, what is the volume of the solid bounded by this surface and on this region, right? Very similar question to the one we have seen for this 1D function. Now we move from the area to the volume. Okay. Then to find this volume, we have the so-called double integral. Okay. And here's the notation. Double integral, so we have two notations of the integral. And D denotes this region where we consider the function. F is the value of the function. And dA means the variance. The letter A means the area. Okay? That's just a notation for double integral. Okay? So in the future lecture, in the next lecture, you will know how to calculate the double integral. But for now, you only need to know that we have application. We can use the double integral to find the volume of solids that I mentioned before. As you can see here, we consider a solid over a region D of xy plane. What I show you, this one, and this double integral gives you this volume. Okay? And it is denoted by this notation. You agree? Yes. So, a very, very nice observation. Let's assume that the function takes the value 1. So you take a look on this picture. When the function takes a value 1, that means the height is always 1. Right? So you have something like a cylindrical, right? With the height of 1. Then you know when the height of a cylindrical cell, cylindrical, is equal to 1, then the volume of this cylindrical is equal to the area of the base. You agree? Yes. That is the idea of this remark. When the function is 1 on this domain, then this double integral of the function 1 gives you the area of the region D. like the base of cylinder, right? You understand? So you will see how to find, how to calculate the integral later. But I just want to show you some example. We also have here some application, but we have time to finish this. So I hope that in the next lecture, the employee will have me to complete this, give you the idea of the application. So let me stop lecture here. Thank you for your attention.
Yes.